always, always, always the first rule of factoring. GCF period. Okay? Your first rule of factoring is always to go for GCF. In this case here, what's the GCF? 2x squared. All right. So we start, take out the 2x squared. What are you left with? Now, here's the little trick. Anytime that you see two terms with subtraction, and one of them's got its squared or the fourth or the sixth or something like that, you always, always, always want to think of it and see if difference of squares happens. Okay? Remember, difference of squares is the first term of perfect square is 16x to the fourth perfect square. Is 1 a perfect square? Is that a subtraction symbol? Did you answer yes to all three of those questions? Yes. So then you can go ahead and do, we get 2x squared, 4x squared minus 1, 4x squared plus 1. So far, so good? Okay. And then you'll notice you should be able to ask those same questions again. Is 4x squared a perfect square? Is 1 a perfect square? Is that a subtraction symbol? Therefore, it is a difference of squares, which gives you 2x squared, and then we have 2x minus 1, 2x plus 1, and then 4x squared plus 1. Now, excuse me, I believe this one just said to factor, right? That's fully factored form. Now, what we're going to start with today is spending more time on zeros. And this textbook likes to go with, start with find all the real zeros and build up to finding all zeros. I just say the heck with it, let's just find all zeros. So I know it didn't say to do this, but let's say it did. When you have zeros, then you have to find your zeros. We know that the terms in the middle, it would have been plus or minus 1/2. You okay with that? Add 1 divided by 2. My 0 here is 0, but what does it have? What do we call that issue? Remember that? Excellent. So this has a 0 with multiplicity of 2. The reason why I say it has multiplicity of 2 is because it's squared. Yeah, it's squared. If it was cubed, that's a multiplicity of 3, and so on and so on. Now, what do you do for the 0 at 4x squared plus 1? What do you have to do? Set it equal to 0. Subtract 1 divided by 4. You okay with that? And then what? Square root. What's the square root of 1/4? I've gone the wrong way. 1/8. Okay. No, 1/8 is 1/2. You said 1/8. 1/2. 1/2 is 1/2 is 1. Okay. But you get x equals plus or minus, because you take the square root of negative, you get an imaginary. So you can write it a couple ways. A lot of times you see it as just I over 2, or 1/2 I, or I times 1/2. Any one of those would be perfectly fine. Because now it was a 6th degree polynomial to start with. The first term was positive, so which way are our tails doing? Up, up, good. They're going up, up. We have 6 possible zeros. 1, 2, 3, 4, 5, 6. Because it has multiplicity of 0. I'm sorry, multiplicity of 2 at 0. So that's where we get the idea that you still have 6 total zeros. Okay. I know we're not doing that yet. We're working our way towards it, but just the more I start showing this to you guys, the easier it'll be longer. Okay. Also on that one, the other one. Bless you. Was there any others in that? Those bless you. That you guys wanted to see? And I think we're sorry. Yes, sir. 39? I'll get yours next, okay? 39, okay. Same basic idea. All right. Now, yesterday we talked about the idea of factoring trinomials. Guys, yesterday we talked about the idea of factoring trinomials the exact same way as we would a quadratic if the exponents kind of followed the same pattern. Notice how the exponent goes fourth, half of that is squared, half of that would be 1. That means I can factor it like I would normally. So what we do is, what times what is negative 36? I multiply the ends together. That adds together to get negative 5. Convenient that the numbers are right in front of you. Negative 9 and 4. So you get 4x to the 4th minus 9x squared plus 4x squared minus 9. You okay with that? Group it. All right? Group it, go with GCFs. GCF of 4x to the 4th, 9x squared is? X squared, very good. Then you have 4x squared minus 9. Over here, we just have a positive 1 to take care of. Are the two things that are in parentheses the same thing? That's always a very, very good sign. So we write it down. And what's left? Okay. One of those you can do something else with. Very good. In the 4x squared minus 9, that becomes a difference of squares. 4x squared is a perfect square, 9 is a perfect square, and it's a subtraction symbol between. So you can do 2x minus 3, 2x plus 3. X squared plus 1 is not factorable because of the plus sign. Not terrible after that. What would change, or I'm sorry, let me rephrase that. What would be your zeros if I said that equal to 0? Plus or minus 3 over 2, good. Is it I or? Plus or minus. Gotta have the plus minus there because it took the square root over an equal sign. Because it's a fourth degree polynomial. What were the tails doing? I think the first term was even, wasn't it? So they're up, up. Okay. Which means it should have how many total zeros? 4. I have 2 imaginary, 2 real. 2 plus 2 is? Okay. What else we got? Anything good? Good. So what I want to do today is continue. We're just going to add some problems to what you guys did last night. But what I want to do today is spend more time working with solves. I want to spend more time today actually going through the motion of finding all of my zeros via factoring. Okay? And what we're looking at, the complexity of the problems we've been doing, it all kind of stays the same. Remember, the textbook at this point will say find the real zeros. I'm going to ask that you find all the zeros. Okay? Okay. Guys, got a bunch of examples here. Now, as you're writing this one down, what should you do right away? Right, no. What should you set? Yeah, set aside equal to 0. So automatically, as you're writing it down, you know you got to bring that 14x cubed over. So I would write down 2x to the 5th minus 14x cubed plus 24x is 0. And then just like every other factoring or solving problem, you always look for what first? And it is 2x. So if you factor out a 2x, you have x to the 4th minus 7x squared plus 12, 0. Before we get too much further, it was a 5th degree polynomial, which means how many total zeros should we come up with? 5. Okay. Our trinomial that we have, x to the 4th minus 7x squared plus 12, that fits that pattern of the exponents matching, so we can factor it like we would anything else. So what times what is 12? You add together to get negative 7. Negative 4, negative 3. Very good. So we have 2x, x squared minus 4, x squared minus 3. It works with anything. If it's 10, if it's x to the 10th, the next one's x to the 5th, the next one is just a constant. Always works. So one of these 3 terms we have here can be factored a little bit further. Yep, the middle one. All right. Where are your zeros? 0, okay. Good. Excellent. Remember, for each term, when you get each term, you can set each one of those equal to 0. Now, what? Oh, remember, when you have, solve for x, we set each one of them equal to 0. I can't factor the x minus 3, or x squared minus 3, so I just set it equal to 0, add 3, take the square root, plus minus root 3. X plus 2 equals 0, 2, so on and so on. Now, this was a 5th, oh, thank you. This is a 5th degree polynomial. No, thanks. 5th degree polynomial, first term was positive. What are your tails doing? Down, up. Okay, so they're down, up. Now, zero, negative 2, positive 2. Yes, ma'am. Every once in a while. Once that I know where someone clean, I'm going to do, just so you get an idea without being overwhelmed. It would be a good idea, so you practice it. Now, square root of 3. Is it greater than 1, greater than 2, less than 2, less than 1? Between 1 and 2. So, tails are down, up. Was there multiplicity with any of these? No, so there's no change in direction. It means it's just going to go through them, change direction, and go and zigzag throughout. Let me rephrase that. Is it changing direction after the 0? Multiplicity, when multiplicity of even amount occurs, you change the direction after the 0. Okay. If the multiplicity is even. Okay. I have an example of think of it this way. Go back when we did this one. Yeah, that's why we're practicing now. Going back to this one, what were your, when you factored x squared plus 6x plus 9, what were your 2 terms? It was x plus 3, x plus 3. That meant your zeros were at negative 3. It had multiplicity of 2. Okay. So when you graphed that, it changed direction at that. If you had if you had x plus 3, x plus 3, x plus 3, that meant you would wind up with x cubed, 6x squared, 9x plus 3x squared plus 18x plus 27. Here, do me a favor. Put these two in your calculator. Y equals? It's okay. Please don't. Pretty please don't. Okay. All right. So what I want to show you here is two different y equals tables. Two different y equals. I want you to put one that says x squared plus 6x plus 9. And then the other one, I want you to put x cubed plus 9x squared plus 27x plus 27. Okay? Because what you should notice where was so see how the blue graph is the regular old quadratic. The other one's the cubic, the down up. See how when it had multiplicity, when it had an odd multiplicity, it went up and through it. That's what that means. Even multiplicity is going to change. Odd multiplicity, it just goes through it. Okay? It's a subtle thing that we do more and more and more as we go on. And I thought it was pretty easy. I thought it was an easy way to show you by just adding an extra term that was the same. Okay? Okay? Find all the zeros in this one. Find all of our zeros for this one now. I have x to the 8th minus 3x to the 7th equals x to the 6th minus 3x to the 5th. What's wrong? All right, move everything to the left side. You want to keep that pressure positive. Now you can do one of two things. Guys, should not have to continually talk over you. You can do one of two things here. You've got 4 terms. A lot of times I've said, hey, if you've got 4 terms, just factor by grouping. Or if you want, you could also do the first thing you would normally do is look for a GCF. It doesn't matter which way you want to go. Me, I see that I have a 5th, a 6th, 7th, 8th. I'm just going to go GCF right away. Just make those exponents simpler. You can, if you wrote it that way, that's fine. It's more traditional to put everything in the descending. That way you don't miss one of the exponent values. So First thing I'm going to do is take out the fifth. So far, so good? Okay. Now, group it. That x to the fifth is still out here. If I put parentheses around these two guys, what's their GCF? In the secondary terms, you have to do make sure you take out the negative. And now you get x to the fifth, x minus 3, x squared minus 1. It was an 8th-degree polynomial, which means you can have how many total zeros? 8. Well, we know this one is plus or minus 1. This is 3. And what's x to the fifth? 0. 0 with how much multiplicity? With multiplicity. Yes, ma'am. You don't have to write x plus 1, x minus 1. If you know it's x squared minus 1, you can just go ahead and write, oh, it's plus minus 1. If it's x squared minus 4, just write plus minus 2. Okay. If it asks you to find zeros, do that. If it says factor, you got to list it. Yeah. Yep, just leave it up there. Yep. If it was just like a 6, and it had no value of x, then it was a scalar. Does that make sense? Hey, real fast, just 1 second. One other quick thing with something like this. If there was like a scalar that was in here, let's say it was like a 4. They all had a 4 into it. I was like a 4x to the 8th, 12, 4, and 12 again. That scalar of 4 has nothing to do with the problem. So even if all of these just had a multiple, not even that x to the fifth, if they were all had a scalar of 4, when you go to factor something to find zeros, the scalar doesn't matter. It's the variables that matter, the x values. Oh, you were asking a question? Yep, that's right. What were you asking? All right. Which one? In here?
Yeah.
Okay. So here we're back in the middle where we're 4 terms. If I group it, what's the GCF of those two? All right. Here, since this was a minus, I do a plus minus into this, which means I take out the -1. And then I get these two guys being the same. That's why I wrote it here. And then these guys were what were left. And it's looked messy because all the different x. What do you got? Is 5 even or odd? It just goes through it. They would just change direction. It depends on what the tails are doing, but it could be like this, or it could look like this, depending upon what the other zeros and stuff were and what the tails ended up as. In this case here, since our first term was positive, it was to the 8th, it would have been up, up. Which means you had zeros at 0, 1, -1, oh, sorry, 3. So tails were up. Oh, crap. Yes, it should have gone through. Sorry. Yeah, I just realized that. So it would have gone down, through. It would have done something like that. It's odd, it goes through with multiplicity and it changes. And don't worry about it so much now. As we get going into it, you'll see that more and more. Yes. Sorry, I just think about what it would look like if it, yeah, sure. All right. You guys do this one. X to the sixth plus x to the fifth, x to the fourth plus x to the third. Because then you have imaginary roots. You only know where the real zeros are occurring at the y-axis. Oh, sorry, the x-axis. So when you know where those real zeros will occur, then later on you can change direction up above or below, and that's where some of this stuff is coming. Yes. Sir. I'm already over here. If I ask you to, here it's just coming to zeros. I'm slowly building into. Good. I don't. There might be one still that I have to show you. Over here. Did that? Did any of you guys just group it right off the bat? I'm gonna group mine like because the last one like this, I did the GCF version. Now I'm gonna group it. You should get the same results if you have right. Yeah, nothing wrong with that. No, it's preference thing. So I take out the x to the fifth, I get x plus 1. Take out the x to the negative x to the third, I get x plus 1. Means I take out the x to the third. It was a 6th degree polynomial, which means we get how many total zeros? 6 of them. I have -1, plus or minus 1, 0. Now, there's 0 has multiplicity of 3. -1 has multiplicity of 2. So the reason why I keep bringing up, and you keep asking, do I do this every time? Do this here? Do I do there? The reason that I keep bringing this up is that eventually you're going to build your own polynomials. And I'll say the zeros are at plus or minus 3i, 6 with multiplicity of 2, and 0 with multiplicity of 3. You'll have to figure out what to do with that. You're starting with the zeros, and you're going to build up to the terms. The idea of understanding the vocab is what this is. This is what kind of all I'm getting at here. Just going to get you used to hearing what it sounds like. I'm trying to map with you. That makes sense. So this is x to the 8th minus 256. Now, excuse me. We know is 8 odd or even? Even, okay? So what are two exponents that you can multiply together that gives you x to the 8th? X to the 4th. So what's the square root of x to the 8th? All right. So is x to the 8th a perfect square? Okay. It's 256 perfect square. What is it? 16. So this is setting you up to be a difference of squares. So this gives you x to the 4th minus 16. X to the 4th plus 16. So far, so good? Okay. One of those two we can go further with. Which one? The minus 16. So we get x squared minus 4, x squared plus 4, x to the 4th plus 16, 0. We can go further a little bit more on one of these. All right. Now, two of those zeros are pretty easy to find. Two others of those zeros are also not too terrible to find. What are the first two zeros that you can come up with without too much of a hassle? Plus or minus 2. Good. These are the easy ones. Minus 2, plus 2. What are the zeros at x squared plus 4? Plus or minus 2, I. Now things get a little bit weird. That. It's 2 and plus or minus 2i because if you said, what's that, Xander? It's plus or minus 2i, guys, because you take x, guys. You take x squared plus 4, you set it equal to 0. Subtract 4, take the square root of negative 4, and that's where we get our plus minus 2i. Okay, Xander? Very good. Now, the last part here is x to the 4th plus 16. We haven't gotten far enough yet to learn how to solve that. It's imaginary. We don't know how to solve that yet, though. So if this comes up, if this is ever up, and I ask you to find all the zeros, you're finding all of the zeros that you know how to do up to including squared terms. If you had a cubic term, you kind of knew how to do that with sums and differences of cubes. But remember that that secondary part, you'd have to use quadratic to get the zeros. Now, if it's just x to the 8th, that just means you have 0 with multiplicity of 8. Or x to the 4th is just 0 with multiplicity of 4. But this one being having a weird imaginary root, there's nothing we can do about it. Now, you guys, you were asking how do you graph imaginary stuff? Well, this just means that it's changing direction above or below the axis. Because when you had imaginary roots before, when you had quadratics, that meant that your discriminant was negative. You still had a quadratic, you could still graph it. It just meant that the vertex was sitting at 2, 3, as opposed to, and it was up. And it didn't cross the axis. It didn't have technical zeros. You graphed those before. All that stuff with graphing like that, if it was above or below the axis, and it was floating up there, or was down below it, and it didn't cross the axis. Those were all imaginary roots. You just didn't realize that's what you were doing. You were thinking about it, but not really thinking about it. It was all in your head. Okay. So again, if this gets to this part here, you just can't do it yet. Yeah, and it's okay. Even though I'm saying find all the zeros, that's all the zeros you technically can do. Unless if this was just x to the 4th, you would say you've got 0 with multiplicity. Does that make sense? Because it's a binomial with that, you can't do it yet. you have to take fourth roots. We haven't learned how to do all that kind of fun stuff yet. It gets into that stuff, yeah, but I didn't want to go into that because then it goes to the 16-year thing. Oh, it's just going to be 2, so you definitely have to imaginary. You wind up with you're right. You wind up with multiplicity at the roots of the imaginary roots. It's not always like that, and I didn't want to get to any. We don't need that now, so we're not worried about that. So, same page from last night, same section. Let's do the. I already posted, didn't I? Was it 69 to 85? Then I want you to do 88. 69 to 85 odds. And then 88 is the word problem one, which is basically straight calculator work. I didn't really have a ton of time to get into the actual calculator part of this today, so we'll finish that tomorrow before we get to division. And it's really simple. It's a lot of table work. It's polynomial word problems are much easier than quadratics because it's usually tables. Right? Yeah, just add it to the sheet from last night, guys. Okay? Yo. I think I already posted it, so. Yep. Tomorrow we'll talk about one of the versions of division. Probably just like long division.